Okay, welcome back, everybody. Here's part two. So remember, in the first part, what you were doing was you had completed a table of values, okay, for the graph that was given of this exponential relationship, and identified that as the x is increased by a constant amount, that the y values were doubling. Okay, so one thing I want us to think about, okay, in particular, is the following. So I want you to notice what happens when x is equal to 0. Okay, so when x is equal to 0, what do you notice about the value of y? So what you might be thinking there is that when x is 0, then the y value is equal to 1. So what's really seemingly bizarre about that is that when you evaluate a power of 2, or any power, to the value of 0, or to the exponent 0, it's always equal to 1. Okay? That might seem a little strange, but here's a little bit of reasoning that can help us to maybe rationalize why, despite the fact that there's a pattern in the table, why it works. Okay? So I want you to study this for a moment. Have a look at this expression here. Okay, so we have 2 to the 3 divided by 2 to the 3. If we expand that out, we'll end up with this expression here. Okay? So 2 by 2 by 2 divided by 2 by 2 by 2. Evaluating, that gives you 8 over 8, which produces a value of 1. Now similarly, remember, okay, we're starting with the same expression, same one as we have up above, okay, same one. But remember what we're doing here is right here, we're applying, right? That's the division rule, or the division exponent law. And that was one where you subtracted the exponents. And notice the value that we come up with. It's equal to 0. Okay, so the rule in this case is that because we started with the same expressions and got the same answers, okay, actually two different answers, right? We started with the same expression here and here and produced two different answers here and here. That means that the following is true. Those two answers must be equal because we started with the same expressions. Okay, so in general, okay, so therefore, any particular power raised to the exponent 0, okay, is equal to 1. And that's a general rule. There are other rules. Okay, in fact, there's one more I want us to focus on. And this is just a rehash or a replay of what we've already seen. Okay, but I want you to consider this. 1 over 4 and 1 over 2. Those could also be expressed, and it seems that it's fading out on me here. Let's see if that's going to come back into view. No. Okay, I'm going to have to write that by hand. Well, that's 1 over 2 squared, 1 over 2 to the 1, and these, of course, remain the same. So we can express the 4, again, as a power of 2. Using the original expression, 2 to the x, what we can say is that it's also equal to 2 to the minus 2 and 2 to the minus 1. Reason being is that I'm simply substituting the value of x in for x. Okay. So there's something really key and important going on here. Okay, so in general, what I want you to see, okay, especially for the top two rows, so for this row and this row, it looks to be as though 1 over 2 to the 2 is equal to 2 to the minus 2. Okay, so it seems like the effect of the negative exponent, okay, is to make a fraction. And this one here, 1 over 2 to the 1, is 2 to the minus 1. So that's the big deal. That's the big idea behind negative exponents. So as far as our reflection is concerned, and there will be a handout on this and some practice to follow this up in the next little while, but here's a little bit of patterning. Okay? So I'd ask that you do study it. If you need to pause the video, please do that in order to make sure you fully understand what's in front of you. Okay? So have a look at the patterning. As we subtract 1 from the power, okay, moving down the table, you can see that we are continuously dividing by 2. And in doing so, that means that 2 to the minus 1 would have to be a half. Okay? Another way to look at it, besides patterning, we have a couple of ways to visualize this. The other way, okay, is to use a form of mathematical proof. So by using a concrete example to justify what we're getting at. So similarly as to the previous example, I'm taking quotient or a division question of 2 powers of 2. I've expanded them out, as you can see here. And what happened is that 2 pairs of 2's have canceled out. One is divided into the other, leaving us with a numerator with a value of 1 and a denominator with a value of 2. Down here, okay, again, using the same expression, but applying the division rule for exponents, we end up with 2 to the minus 1. So because of that, because we started with the same expression, producing 2 different answers, those 2 different answers are equal to each other. Okay. So the grand finale, of course, would be a general rule. Okay. So again, remember to pause, take notes if you need to, but I will provide a copy of this last slide as it is quite detailed. So in general, this is your negative exponent rule. Okay. So if B is any real number, okay, and a real number basically meaning any number, okay, as far as our definition of number is concerned, other than 0, okay, so we're going to use as our base non-zero values, okay, and n is a natural number. Now, natural, okay, what that means is more or less the counting numbers, okay, the counting numbers. In fact, you can also use 0 as a whole number. That works too, but generally speaking, we'll keep it to the natural numbers or the counting numbers. So this is a truth. So you can create a fraction out of the power. So more or less, drop that power, which you have here, into the denominator and change the sign of the exponent. Okay? Notice how the exponent flips from a negative, and that sign is dropped here in the denominator. The converse is true too. So if you start with a fraction that has a negative exponent in the denominator, what you're going to do is you're going to flip that and you're going to express it as a power with a positive exponent. Okay? So coming up after this, not within this video, will be some guided examples and a little bit of practice that you can use to make sure that you fully understand and can apply the concepts of 0 and negative exponents.